Welcome to week 5 of KF52 Software Engineering Practice, and in particular the Artificial Intelligence stream. In this lecture, we are going to focus primarily on two things. Firstly, I'm going to introduce you to convolutional neural networks, and secondly, I'm going to explain to you how you can do engineering on your neural networks so that you can squeeze out as much performance as possible. So this is going to be mostly in two parts. The first is the convolution, and then second is a bunch of different tricks that you can use to improve performance. So in this video, I am going to give a very brief recap of neural networks and then explain the sort of code structure that I expect to see from you when I go through the projects that you submit. And the bulk of the lecture is going to be introducing convolutional neural networks, followed by engineering neural networks, which is going to involve dropout, it's going to involve batch normalization. We're going to discuss different activation functions and the loss functions that are going to impact on back propagation. Then we're going to discuss data augmentation, how you can get the most out of your data to train neural networks. And finally, I'm going to show you a coding example for how you can put all of that together very quickly, very succinctly within one convolutional model. Firstly, I want to remind you that our goal with neural networks, with deep neural networks, convolutional neural networks, really with machine learning in general, is to learn new representations of data to make it easier for a classifier to understand. So this is an example that we saw in lecture 4. I'm not going to go back over it, but you can see how with having shifted the axes to two new parameters, we can much easier define a decision boundary on the data represented by polar coordinates rather than data represented by Cartesian coordinates. And we're trying to do this with neural networks, but to a much more complex degree. And we can build from one layer neural networks towards deep neural networks by simply adding more and more of these hidden layers. So in this example, we've only got 3 hidden layers, but you can go as far as having 100 hidden layers. The largest I've seen has got like 1200 hidden layers, and you can still get reasonably good performance. So absolutely, you can play around with making these networks deeper and deeper and deeper and see how your performance changes based on the depth or the number of neurons that you have. This lecture is going to focus on a few different ways that we can improve neural networks. So with regards to pre-processing, we are going to look at data augmentation. And we're going to look at different loss functions that we can potentially use when we are, or to get a better performance out of our network. So a loss function is defined by this squiggly L. And finally, we're going to really hone in on these hidden representations and look at some of the different things that we can do with those. So some of the operations that we can apply to these hidden representations to make them better effectively. So firstly, we'll look at activation functions. So stuff like ReLU, and then the activation function in the output layer is going to be sigmoid or softmax. And we're also going to look at things like dropout, where we remove some neurons, and batch normalization. Okay, so that's all coming later on. First though, we're going to go into convolutional neural networks, and you can see that there's an element of a regular neural network right at the end of a convolutional neural network, but convolutional neural networks are built mostly out of these convolutional layers, which are designed to get the most performance when we're looking at images specifically. So this is a two-dimensional convolution, but if you're dealing with videos, maybe you want a three-dimensional convolution. If you're dealing with words, or if you're dealing with time series data, maybe you just want to convolve in one dimension. So I'm going to explain that in the next video. For now, I just want to go over code structure. So you'll usually have a train or a test.py, but sometimes they can be all in the same file called main.py, and that's where you're going to tell Python that you want to do testing and training. We usually have our model, or if we have multiple models, we usually put them in a separate file so that they don't get in the way, basically. It's much more convenient to not have to skip past all the different layers that you have. Particularly if you're working with deep networks, this can take up a lot of code, so it's much more convenient to have it in a different file. Then we can use common utilities that we might be looking to, like if we have functions that are useful both within model.py and main.py, in other files that we're using, it's nice to have just this utils file which stores all of them, so they're easy to link to. And then an additional one for arguments. So these usually have your hyperparameters, and we have that again for the same reason, so you don't clutter this main.py and keep that as clean as possible. Sometimes you'll have other ones depending on the sort of work that you are doing, but these are the four that I would really recommend that you always have, or maybe a fifth one if you're having test.py and train.py as being two separate files. Yeah, so this just helps you structure your code, and it's actually a lot easier for us to read as well if you do it this way. So I highly recommend having these separate files. And yeah, there's loads and loads of open source deep learning code on GitHub, so have a look through that. I want to talk to you about these arguments, or sometimes we call them parameters, just because they're very, very useful when it comes to your iterative development mission and when you're trying to get the best performance out of your network. This lecture is going to go in depth into how you engineer your neural networks. So this is kind of going to set up the baseline for how you can adjust different parts of your model very, very quickly. So we start off by defining different arguments that we're going to have. So this might be the number of epochs that you use, the number of neurons that you have in each layer, the number of layers that you're going to have. And then we are going to do this line where we do args parser.parseArgs, and that is going to give us this object called args, which is going to store all of these arguments that we've defined at the start of our code. So the benefit of this is we don't have to go into our code and change lots of different things, right? Like every time we want to try something new, we can simply run the file with the Python main.py, and then we use this dash dash to suggest that we want to use a certain argument, and then we define the argument. So in this case it's the name, in the next case it's the number of epochs or the number of neurons, and then the next thing is the new actual parameter that we want to use. So if we want to have just 10 epochs, rather than going into the code and changing anything manually, you can just run this script, but replace 100 with 10. And this is just going to make everything a lot faster for you. The other thing that I'd recommend is to have something which is going to print out your arguments at the end of your code when it comes to printing your test set, and this will let you know exactly what performance, like what parameters you had that got you to that performance. So I've had it so many times where I've just altered something manually and got the best result, and then I play around a little more and try to improve on that, but it gets worse, and then I've forgotten how I actually got the best result that I got, and that can be completely eliminated if you print out the arguments that you're using. So that's something that I also very, very highly recommend. That's it for this video. Next video we're going to look at convolutional neural networks, so I will see you there.